AB students, how are you? I hope you had a good weekend, or depending on what kind of weasel you are, you might be doing this Wednesday, although I'm recording it Tuesday. Our test is in a week or less if you're watching this Wednesday, and we're going to take this week to get you polished up and ready to kill it. So here we go. This sheet should have been available on the website for download, or you can basically just write this in note paper. As far as outlining, you don't have to copy all these topics according to the College Board, but you should pay attention here. All right, so these are the applications of derivatives that you need to be able to use or do. The mean value theorem, remember the big idea here is that there is a place where the average rate of change equals the instantaneous rate of change. And so something like that. If we were to look at that analytically or to look at this graphically, if I had an average rate of change between two endpoints, the slope between the two endpoints, there's got to be a place where the tangent slope is the same. In this case, there would be two places. Remember, the conditions are that the function must be continuous on the closed and differentiable, or the derivative exists on the open. All right. The extreme value theorem, global versus local extrema critical points. Let's start with critical points. Critical points are points x is in the domain where the derivative is zero or doesn't exist. They are the first thing you look for in terms of finding extrema. That's possible candidates. Now, the extreme value theorem says that if a function is continuous on a closed interval, so they don't let it grow forever, then it must have an absolute max and min, or global max and min. Global and absolute are synonymous. All right, so a function is increasing or decreasing where f prime is positive, and so on. The first derivative test, let's say it well. Make sure you say it well, all right? First of all, f, be careful with your subjects and your nouns and pronouns. F has a max if f prime changes positive to negative. Okay, be careful, use f and f prime in the correct place, etc. Candidates test to determine absolute extrema. That's the second part of the EVT. Absolute or global extrema must happen at endpoints or critical numbers. Those are the only candidates for where absolute extrema could occur. Concavity, we know that concavity comes from the sign of f double. Using the second derivative test, let's get the wording again here right, all right? For example, you might say, you could conclude max or min, but let's just do max. F has a max at x equals c because f prime at c is 0, making it flat, and f double at c is positive, so concave up. All right, now that part I just gave you at that, actually concave down. I just screwed it up in so many ways. So what if I said f double is negative, so concave down? Now that right there I just added, that's the worst. I just screwed it up. I ruined it. I just took my point and gave it back to them because I wasn't careful. I thought I was impressing people, saying, hey, look, the second derivative, I know it's concave. That's garbage. Reread it again. What's the subject of concave down? It says because the derivative is 0, the second derivative is negative, so concave down. What's concave down? The function, the first derivative, the second derivative? What are you talking about? So don't add garbage, okay? You're not impressing people. You're ruining math. So f has a max at x equals c because f prime is 0, which makes it flat, and f double is negative. Period. Full stop. Nothing more, nothing less. Say what needs to be said. Period. Okay? Sketching graphs for the functions, you should know, based on the first derivative being positive, tells you increasing or decreasing, and the second derivative Sine tells you concave up, concave down, horizontal tangents and stuff. Same deal with first derivative, second derivative. Optimization, if they give you an optimization, it'll be something you can handle, no problem. So start by saying, what are they optimizing? What's an equation for that? That's often the hardest part. Get it down to 2 variables if possible. And then do your calculus for max or min. That's when you're home free. Okay. You could also see related rates problems, and that to me is an application as well. Optimization problems, we already covered that. And then exploring implicit. Remember, anytime you have something that fails the vertical line test, that's called a relation, not a function, all right? Circles, ellipses, hyperbolas, and so on. It often is the case that when you take the derivative here, it is a function of x and y in it. Yeah, like a circle might have, right? It's important to note that if the slope is 0 over non-zero, then that's no rise, but some run, and so that is horizontal. If you get non-zero over 0, that's rise, but no run, and so that is vertical tangent, not asymptote, vertical tangent, all right, let's practice a little bit here, shall we? Now I remind you the practice idea is you try the question on your own, pausing the video, and then when you're ready, hit play, and if I give you the answer and you got it, then move on to the next question and don't worry about listening to the explanation. But if you missed it, then get out the red pen and make corrections and learn from your mistakes. So will you try this question? I'll call it number 1. Try that on your own. Pause the video. Okay, so I hope you circled 1 and 2. If you circled 1 and 2 but not 3, then you're good. Move on to the next question. If you didn't know what to do, then let's go over it here, all right? So you've got this crazy function. Who knows what that looks like? On a closed interval, 0 to 5. Closed interval, okay. The following letters, which the mean value in the theorem apply to? So for the mean value theorem to apply, it must be continuous on the closed and differentiable on the open. All right. Now, continuous would be a problem here in this case because sine cannot equal 0, or else we get a 0 in the denominator and a vertical asymptote. So we're probably going to have problems at 0 and pi and 2 pi and so on. That's our discontinuities, our continuity problems. Now, in terms of 1 to 3, 1 to 3 does not include 0, nor does it include pi, so we're good to go. 4 to 5, same deal. 2 pi is 6.28-ish. So 4 to 5 is also okay as far as continuity goes. And then 1 to 4 is out because it includes pi, and there's a vertical asymptote at pi. So that's why I scratched 3. I did look at differentiability, and though I didn't particularly want to take the derivative, I didn't actually take the full quotient rule. I just said over the square of what's below would be a problem where sine squared is 0, but that's the same place, isn't it? So it didn't add any information. All right. Try 2 now. Try 2 and see what you get. And pause the video. Okay, so extreme value theorem guarantees absolute min and max if it's continuous on a closed interval. It must. If you can lift your pan and they end it so it doesn't go to infinity, then it must have an absolute max and min. Must. All right, so this would be having some continuity issues at 2 and -2. So I need to find an interval without those in it, and then I would be good to go. Well, these definitely, this is like -6 to 6. That involves those vertical asymptotes. So if you think about it here, it's going to go crazy at 2, and therefore that's not going to have an absolute max. That's no good. Negative 2 to 2, that's awesome, but it is inclusive of the endpoints, and I don't want to include the endpoints because I have asymptotes at 2, and so if I included 2, it would not ever reach a maximum or a minimum. Negative 1 to 1, that's good because it does not involve those asymptotes, so I think we're cool there. And this involves, this is like 1.5 to 3, so it's got a vertical asymptote at 2 in there. That's no good, so it's C. Okay, shoot, I forgot to give you the answer first. My bad. All right, try this one. Pause the video and I'll give you the answer. Okay, the answer to this is B. If you got B and you knew exactly what to do, fast forward to the next question. If you didn't get B, then let's get out the red pen and make corrections. All right. So this has all 3 existence formulas in it. There's 3 theorems about existence in calculus that we've covered. Intermediate value theorem says there must exist a y value between other y values given. Mean value theorem means there must exist a place in the curve where the instantaneous rate of change equals the average rate of change. And extreme value theorem says there must exist a maximum and a minimum greater than or equal to all other values, all right? For intermediate value theorem and extreme value theorem, all that's required is continuity. Mean value theorem requires differentiability. Now they give us continuous, but not differentiable. This 5 here, IVT, okay, it's continuous, we got that, and the 5 they ask about is in between. So yeah, that's a yes. That's got to be true. We know nothing about the derivative having to equal 4. I think they're trying to bait me into saying, yeah, the instantaneous rate of change there is 4, but I don't know if it's differentiable. So the curve could have an average rate of change of 4, but have this boop, boop, like this, in which case there is no place where the instantaneous rate of change equals the average rate of change. So that's the one because it requires differentiability, which we're not given. All right, the free response. This should take about 10 to 15 minutes, so pause the video, get this done with quality, and we'll go over it in a minute. Keep in mind here that they've got 2 functions going on. Read carefully. This is the graph of G, and they give you f prime. So it's 2 different things going on, all right? Good luck. I'll talk to you in a minute. Okay, sorry, I should have told you this is not calculator active. You may not use a calculator on this. All right, so A, find the x-coordinate of each critical point of F. Classify each critical point as the location of relative max, relative min, or neither. All right, so first I start talking to myself. Critical points are numbers. X is in the domain where F prime is 0 or undefined. The domain, they don't give us, so I assume it's defined for all reals. So let's go. The derivative, if I factor it, is, remember, this is already a derivative, so I don't need to take a derivative again. So if I take an x out, I have x times 6x minus 5 times e to the x equals 0 or undefined. So the critical numbers are 0 and 5, 6. E to the x cannot be 0, so that yields no critical numbers. So as far as a sign test to see what's going on there on the derivative, 0 and 5, 6. If I look at -1, I have a negative, and a positive. E is always positive, so that's positive. If I try maybe a half, I get a positive, a negative, and a positive, so that's negative. And if I try 10, a billion, positive, positive, positive. All right, so let's make our conclusions using the first derivative test, relative max, min, or neither. If the derivative goes positive to negative at 0, then the function goes increasing to decreasing at 0, so we have a max. And by we, I mean f. F has a max at x equals 0 because on the AP test, abbreviate nothing. because f prime changes positive to negative. You can use the symbols, and then if you're interested, if you're pinched on time, go for it, but if you have time, prefer to do it all things well. All right, the derivative goes negative to positive at 5, 6, so f has a min at x equal 5, 6, because f prime, darn it, it's hard not to use symbols, f prime changes negative to positive. All right, pretty straightforward. All right, B, how'd you do? Check your work. Did you say B has a point of inflection at, oh, where is it? Did you say F has a point of inflection at 1/2 and negative 5/3 because F double changes sign there? If you did, then feel free to move on. You probably understand just fine, all right? So points of inflection are where F double changes sign, not a 0. F double changes sign. So you'll need F double. And let's use the product rule. First stays the same. Derivative of the second plus second stays the same. Derivative of the first. There's your second derivative. Let's clean it up. Here's algebra time. Let's take out an e to the x, and I'd have 6x squared plus 7x minus 5. Factoring. Hope you can factor that, or at least solve by the quadratic formula to find the zeros, but it does factor 3x and 2x. And I want a 10 and a 3, so 5 here and a 1. And I want the 10 to be positive, so I need that positive and that negative 3. All right, so that's where I get my zeros of negative 5/3 and 1/2. I did verify that the second derivative changed signs there. How it changes signs in this case doesn't matter. It matters in the first derivative test how it changes sign for max or min, but for inflection it doesn't matter how it changes sign. So you would say F has inflection points. You could put them together. X equal negative 5/3 and x equal 1/2 because F double changes sign there. All right. For C, hopefully you have negative, 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 positive. It did say explain why. I said, now keep in mind here, we're talking about G here. So you're looking at this graph now, not looking at the equation anymore. Switch gears, read carefully, switch gears and say, oh, G, okay. So there's G, there's the graph of G. And I think you'll agree that the graph is always decreasing. And so G double is negative because the graph of G is decreasing. Or you could say the slopes are negative there, tangent slopes are negative. This negative here, I say that the second derivative of G this negative here, the second derivative is negative there because I circled the wrong thing. First derivative is negative in both places because the function is decreasing. The second derivative is negative from negative 3 to negative 1 because the graph of G is concave down. And in this case, the second derivative is positive because the graph of G is concave up. All right. And last but not least, now this was the only one that I thought was kind of rough. I had to do some thinking on one of the pieces. All right, so H is defined as the product of F and G. All right, I got that. Is H increasing or decreasing? 5. Well, I need to know, is H prime positive or negative? That's really the question. So let's start by finding H prime. h prime of x is first stays the same, derivative of the second, plus second stays the same, derivative of the first, product rule. And now I need to figure out what about all these things sign-wise. Now, f of x was actually the hardest one, so I'm going to come back to that. G prime on 1 to 5. Well, G prime, the graph is of G is decreasing, so G prime is negative because the graph is decreasing. All right, so I got that sign's negative. Cool. G on 1 to 5, that's just is the graph above or below the axis. And that's negative because the G graph is below the axis. F prime, which is e to the x times 6x squared something or other minus 5x, is positive by our sign chart back in the day, or for any x between 1 and 5, that comes out positive by sign testing. And last but not least, let's go back to f. All right, so again, I don't know f. I know f prime is e to the x 6x squared minus 5x. If you read carefully, you also know that f of 1 is 3, I believe. Yeah, that's given right here. All right, so then I'm thinking, all right, so does that mean I use the fundamental theorem and I have to integrate this? Do I use this? If I had a calculator, I could easily do this, but gosh, do I have to integrate that? And then it's integration by parts, and ooh, mess. No, that's not necessary. So here's the deal. You know that at the start of the interval, at 1, f is positive because it's at 3. And what do you know about what f is going to do after 1? Well, we just said that f prime is positive, so it means f is going to increase. Well, if it starts at 3, a y value of 3, and only increases, doesn't that mean it's got to be positive? So you would say this is positive because f at 1 is 3, and f prime is positive, so f is increasing from 3. All right, so then back to h then. I have that this is positive times a negative plus a negative times a positive. That's a negative plus a negative. And so h prime is less than 0. From that I conclude h is decreasing. All right, that was the humdinger of the bunch. All right, get yourself a little drink or a little snack and let's go over Unit 6 in a second. Oops, I totally lied to you. There's one more free response before we're ready for Unit 6. My bad. Okay, so this is not calculator active. I know it's tempting to pick up the calculator, but you should not need a calculator here. All right, so here goes. The number of fish. Read the problem very carefully first. Don't be in a rush. I know it's going to feel like that ticking clock on the AP test means you got to go, go, go. But it'll all be wasted time if you don't know what the problem's about. So read carefully, please. The number of fish in a small bay is modeled by this capital function f, 10 times this cubic function, okay, where t is measured in days from time day 0 to day 8. All right, I got it. A, using correct units, interpret the meaning of, I think that's f prime. The other tick looks like it's part of the f. Excuse me. So f prime, f4 is negative 30 in the context of the problem. All right, give that a go and we'll go over it. Okay, so f prime at negative 30 is this, at 4, is the same as df dt. I don't like prime notation when I go to interpret derivatives. I like to think of it as a rate or a ratio of change. So it's change in fish, d is delta, tiny delta, change in fish over time. And so this means at time equal 4 days. First of all, make reference to that. That's got to be in your answer. The number of fish, make sure your handwriting is legible, in the bay is, don't say changing, you need to do more and say you understand the sign, is decreasing at a rate of, that rate of usually comes in a derivative interpretation, 30 fish per day. You wouldn't say negative. The negative is in the word decreasing, so just 30 fish per day. All right? Try B, and then we'll go over it in a minute. Okay, so for B, did you get 1,000? I got 1,000 with a lot of EVT work. So if that's the case and you think you killed it, no problem, move on to the next piece. But if you'd like to go over it or you didn't get 1,000, let's get out the red pen and make corrections. All right. So let's start at the absolute min. Not relative. I shouldn't be saying F prime goes positive to negative there. That's the relative extrema test for relative extrema. Absolute min, you're going to say something like absolute min occurs at endpoints or critical numbers. The endpoints are obvious. Two candidates are time 0 and 8. The critical numbers are where the derivative, capital F, is 0 or undefined. So I guess we're going to need to start by finding capital F. The coefficient, you know, you can leave that out front and focus on the variables. The derivative of the interior is 3t squared minus 24t plus 45 plus 0. I took out another 3 and then opposed to the other one, this one factors really easy. So it's t minus 5, t minus 3. So my candidates or critical numbers are 3 and 5 along with the two endpoints. So now I just need to fight it out, let the candidates fight it out and see which one is the least of them. F at 0, now you're going back to the original function. So if you put in F at 0, I got 1,000. I was working without a calculator here, so I hope I did these correctly mentally. F at 3, I have 1,540. Keep in mind, as you go, you're talking a cube, a positive cube shape with two endpoints. So really, the minimum, I kind of know in my head, the candidates for minimum are 0 and 5. But I'm going to find all 4 candidates and just verify. I really just need to know which one goes lower, 0 or 5. But that's right. F at 5 is 1,500. And so it did not go very low. It's more like that. And F at 8 is probably more like a max. And I got F of 8 was 2,040. From that, I conclude the absolute min is, make sure you answer the question. And they say, when is the absolute min, or what is the absolute min? And they say, what is the absolute min? So please don't say, the absolute min is at time 5. That's not the question. They didn't say when, they said what. The absolute min number of fish, or times 0 I should have said, is 1,000. Because it's the least of the candidates. So if you wanted to say because 1,000 is less than 1,500, which is less than 2,040, because it's the least of the candidates. All right. Try C. Okay, did you say for C that the rate of change is decreasing on 0 to 4? The rate of change decreasing means that the derivative is decreasing, and that means the derivative of the derivative is negative. So you should have looked for the second derivative. You could go back to the original function. I went here and took the derivative, which is 2t minus 8, which has zeros at 4 and before, as far as the f double, it is negative and positive. So from that I conclude F is decreasing. The rate of change is decreasing. Rate of change is decreasing on 0 to 4 because F double is negative. Okay, do not expect them to read your sign chart. Say it in your statement. All right, and then D. Try D. This is the hardest of the bunch. Okay, so this one, just a warning. I don't know if the AP test, they're going to add several parts and make one part really nasty and really abstract, and you maybe not even make headway, but get into it and connect something. Show you know something if you can, but definitely do it last so you get the layups first, okay? So, the number of pelicans flying near the bay is modeled by the differentiable function P, where P is a function of the number of fish. So P depends on the number of fish, or relates to the number of fish, which is the fish function we are. I guess that makes sense. Okay, that doesn't mean it's equal to the number of fish. It might be twice the number of fish, or the square of the number of fish, or the 3 times the number of fish minus 2. It's some kind of depending on the number of fish. So pelicans depends on the number of fish. It's got some kind of F in it, and who knows what else is going on. I don't know. But pelicans is a function of the number of fish, which then in turn depends on time, all right? So pelicans depends on the number of fish. All right. So if I wanted an expression for the rate of change in the number of pelicans, then don't I need to take the derivative of that? The rate of change of pelicans. So it'll depend on, the equation that relates fish to pelicans, but also then the fish equation itself. So chain rule, all right? So you needed to use the chain rule here. The rate of change in P then would be the derivative of the outside with the inside the same times the derivative of the inside. Now, I was pretty confident that was right, but then I thought, oh, maybe not. So I looked up their answer, and I think I would have lost a point because the concept is good, but they wanted you to go all the way and say, all right, then put these in. So F is the 30 times the cubey kind of thing, and F prime is the 30 times the squaredy kind of thing, and actually show F of t and F prime of t in. So the big idea though was use the chain rule. You had to use the chain rule. All right, that was a tough one. All right, now get a snack before we go to Unit 6. All right, so here we go with Unit 6. Unit 6 is the introduction of the definite integral. So, or actually integration, not just definite integral. All right. So, exploring accumulations of change. Wow, that's so big. So, the big idea, one of the big ideas of calculus is that if you have a rate of change, whether it be people per minute coming into the place or a car going at feet per second or something like that, then if you look at an area in that calculation, then this is a rate times a time calculation, and that area under the curve really represents amount of change. If you did people per minute for 4 minutes, then you're going to get people. Or if you did, he does 20 problems per minute for 17 minutes, then you're going to get problems. So area represents change in the amount, all right? So total area then is accumulation of change. net change. Could be an increase or a decrease. Total change theorem, some books call it, all right? All right, cool, now I get that. In terms of finding the area theoretically, you could, if you go to f of x kind of notation here, the area is a base that's delta x and a height that's f at different points. Yeah? All right, and then that's just one rectangle, and you have to add many of those rectangles. Now, remember then that delta x comes from how wide the region is divided into however many chunks. The x at which you draw a height, why did I draw it this height? Well, it depends on two things. Where you started and how many delta x's you've gone over. All right. Now, if you then take the number of rectangles to infinity, so they get smaller and smaller and smaller, you get a better and better fit. And you do that by taking a limit. What happens is that goes to infinity. Now, one aspect then of the fundamental theorem of calculus is to say, well, the infinite sum of this then becomes this accumulation of change, infinitesimally small changes, and that's the fundamental theorem slash the definite integral, the accumulation of change over an interval. Now, keep in mind that this, again, accumulates change. It doesn't equal amount. If you want amount at some certain time, amount at time x, you have to keep in mind a starting amount and then talk the change up to a certain point under the rate of change, all right? So if you want amount, it's initial plus change to get amount at a certain time. If you do a definite integral only, that's only change. All right. Properties of definite integrals, you can split a sum, but not a product. You can, you can put out coefficients, but not variables. Remember, algebra-wise, this is not so much a property of definite integrals, but if you have a sum in the numerator, that you can split. Algebra allows that. But if you have a sum in the denominator, that's 100% no, you cannot split that. That's a no-no. All right? Also keep in mind that if you switch the limits, it's switch the sign, yeah. That's very valuable also when you want to go backwards in time. Definite integrals, check. Fundamental theorem of calculus. I mean, gosh, this is a very common free response, but if they said something like this, interpret this, whatever it might be, the very first thing you should be doing is saying, oh, by the fundamental theorem of calculus, a definite integral is the antiderivative at the upper minus the antiderivative at the lower. Fundamental theorem of calculus. I mean, you've got to know that, all right? Finding those antiderivatives requires some big skills, the most obvious of which is the power rule. Remember, it's raise the power by 1 and divide by the new power. Don't forget the plus c, senor. All right, keep in mind that that applies to all powers with the exception of x to the negative 1. That involves just log. But anything else, any fraction that's not 1 powered is power rule. Okay? You've got to be able to use substitution. Make sure you, besides making the substitution, make sure you change the dx and you balance and find the changes that go with that. Change the limits if it's a definite integral, or sub back if it's an indefinite integral at the end. Okay, use the initial condition to find the plus c. integrating functions using long division and completing the square. This is not a huge idea, especially for a small exam. I don't know if this will come, but if you had a rational function where blah, 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 if these powers, if the top power is as big or bigger than the bottom power, then you must divide first before you go to integrate. Okay. These purple ones are BC calculus topics only. Integration by parts is not on the AB exam. That's a pity because you guys are really good at that, and these don't mean much to you. All right, and then techniques of antidifferentiation. You gotta know how to take an antiderivative. I mean, that's a lot of skills there, whether it be U sub or splitting fractions or antidifferentiating sine, cosine, E, tangent, all this good stuff. You've got to be on your game technique-wise, all right? All right. Here are two practice questions. Would you give these a go? They were very frequently missed on the practice multiple choice questions you did. I'll pause the video and we'll go over them in a sec. Okay, so your answers are D and D, I think. Did I get that right? D and D are my answers. So if you agree with D and D, cool. Otherwise, go ahead and move on to the next question. But if you didn't get D and D, then let's talk about this. All right. So which of these followings Riemann sums, or sum of infinitely many rectangles, is equivalent to that definite integral? Now let's start by limiting choices here. All right, delta x has to be 5 minus 2 divided by n rectangles. So I should see a 3 over n. This can't be it. This is good. This can't be it. This is good. Those two are still in. All right, now remember the height at which you draw depends on where you started from plus how many delta x's you've gone over. Now the function then is 1 plus where you started from plus how many delta x's you've gone over, because the function is 1 plus whatever x you put in, yeah? So I'm looking for something with 1 plus 2 plus blank to the fourth, and that is this guy, not that guy. All right. Now maybe this one will make more sense here. Same deal, the delta x first. Delta x is 3 over n, so that's gone, in. Those are still in. The function is arctangent of 1 plus whatever the x is, and remember the x depends on the start plus the change. The start was 1, and the change, the number of changes, so I'm looking for something like 2 plus 3 over n so many times, and that is that guy, not this guy. It was tempting to say 1. They almost got me because, you know, I thought, oh, see, they're starting at 1. That's cool. But the function also had a 1. So you're looking for 1 plus the starting value, which is 1. So that's why 2. All right. Try this one. You may use a graphing calculator. Feel free to take about 15 minutes, and we'll go over it in a second. Okay. Let's see how we did. Oops, let me get my key, just a second. Okay, so, sorry, here we go. Looking at your results, for A, did you get 0.6805? B, did you get 0.3415? C, I hope you said the trapezoids or an underestimate because the second derivative is negative, and therefore f is concave down. I think if you just said the second derivative is negative, that would be fine, but if you just said f is concave down, that would not be fine. You would have to use the second derivative to justify. And then the last piece is the limit as, so let's just go through it here. So remember, you're taking many of these guys, starting with I representing the first rectangle and n representing the last rectangle, but letting the rectangles go to infinity. You could also use k, I suppose. All right, and then remember, x sub I depends on two things: the start plus the number of delta x's, and number of delta x's is the counter I. So hopefully you did something like this. Oops, have it. Delta x, in this case, delta x was the total region from 1 to 3 divided into n chunks, so that's 2 over n. The function, I didn't know that you use f or the cosine, so they can't nail you for being too exact, so I'm going to say the cosine of the square root of, and then I'm going to be clear what x I'm marking at. So each time I go, my first rectangle would be here at 1 plus a single delta x, because I'm using right. The second would be 1 plus 2 delta x's. So generally, x sub 1 is 1 plus 1 delta x. X sub 2 is 1 plus 2 delta x's. So x sub I is 1 plus I delta x's, and delta x is 2 over n. So that's your answer, the last one. All right. Now, if you killed those, great. If not, then pick up your red pen and let's go make corrections. I think that's the last of it. So if you did smoke that, congratulations, you're done for the day. I'll see you tomorrow. All right. For those of you who need to make corrections on A, let's talk about this. Let's go with, they're saying midpoint rect. So midpoint. So I'm starting with a region between 1 and 1.6, and the midpoint then is halfway between, so that's 1.3. So I'm going to use a delta x of 0.6, and then the function at the midway point between those two, f at 1.3. The next region is from 1.6 to 2. Halfway point is 1.8. So the next delta x is 2 minus 1.6, or 0.4. And the height I'm going to use is midpoint between those two, f at 1.8. Then finally, 2 to 3. Midpoint is 1.5. Okay, so the total region width is 1. 3 minus 2 is 1, and the height at f of 1.5. Throwing that into your calculator, making sure you have, this is an approximation, and they would take 3 decimals of 681 or 680, rounded or truncated. All right, B. Let's talk about this. Is this a trapezoidal rule case where there are equal subdivisions and you can factor out a delta x and do this 1, 2, 2, 2, 1 stuff? And the answer is no, they're not equal subdivisions. As you can see, it goes from 0.4 wide, 0.6 wide to 0.4 wide to 1 wide. So it's a no, and you're instead going to use 3 trapezoids. All right, so the first, the bases are f at 1 and f at 1 1.6. Those are the parallels. The height, which is the distance between the two, is 0.6 divided by 2. The next trapezoid is f at 1.6 and f at 2 for the bases, or the parallel sides, and the height, or the distance between the two, is 0.4. And finally, the last, let's go this way, is going to be f at 2 plus f at 3 times the base of 1 between the parallels divided by 2. That's right, got my answer. Make sure you use f when it's appropriate, g when it's appropriate. Read carefully, please. This is tempting to just graph the function and say, hey, see, concave down. But that, what looks like concave down doesn't necessarily prove concave down. So I actually graphed f double and found that f double is less than 0 on 1 to 3. And from that I concluded f is concave down on 1 to 3. Then I used a well-known fact with a picture of if f is concave down, then trapezoids will definitely underestimate the true area. So I said trapezoids will underestimate because the curve is concave down. Okay, and then the last one I kind of explained already, so I think we're good. Hopefully that went well. I will talk to you tomorrow, people.